Welcome to the Deep Dive. Today we're tackling a really core subject for modern aviation maintenance. All the electronic and digital systems that, well, keep these incredible machines flying safely.
That's right.
And our goal here is really to pull out the crucial bits about digital techniques and electronic instruments, the stuff that matters when you're actually working on the aircraft.
Exactly. Yeah, that module's dense, packed with information. But we want to do more than just define terms. We're aiming to give you a clear, hopefully engaging look at the principles, the components, and how it all comes together in the sophisticated systems you see every day.
Right. A focused look, like you said, into the digital backbone.
Precisely, without getting totally overwhelmed by all the detail.
Okay, let's dive in then. And I guess the place to start is the absolute basics, the language these systems use, and how they translate things from our analog world, numbering systems and data conversion.
Absolutely fundamental. You really can't get away from binary. It's the native language, machine language, just zeros and ones, base 2. And each position, moving right to left, is a power of 2. So like the binary number 0011, that's, let's say, 1 times 2 to the 0 plus 1 times 2 to the 1, which just gives you 3 in decimal. Pretty simple concept at its core.
Okay, that makes sense. But the module also talks about octal and hexadecimal. If binary is the base language, why bother with these others?
Yeah, good question. It's really about practicality. Binary numbers can get super long and, frankly, pretty unreadable when you're dealing with, say, memory addresses or complex data.
Right, pages of zeros and ones.
Exactly. So octal, which is base 8, and hexadecimal base 16, they're just much more compact ways to represent those long binary strings. And because 8 and 16 are powers of 2, converting is easy, you just group the binary digits. 3's for octal, 4's for hex.
Okay, so it's like a shorthand, makes it easier for humans to read and work with.
Pretty much. A massive convenience for programmers, engineers, technicians, reading documentation. It just makes handling the underlying binary much less painful.
Gotcha. Okay. What about BCD, binary coded decimal? Is that just another way of writing binary?
Not quite the same as standard binary. It uses binary digits, yes, but with BCD, each decimal digit gets its own 4-bit binary code.
Oh, okay.
So if you take the decimal number, say 82, in BCD, the 8 is represented by 1,000 and the 2 is represented by 00 zipple. So you'd write it as 1,000,0000.
I see. So it keeps the decimal structure almost.
Exactly. You don't treat it as one big binary number with place values across the whole thing. Each decimal digit is separate. You might find it in maybe some older display systems or specific interfaces where that direct decimal link is useful.
Interesting. Okay, so we've got ways to represent numbers digitally. But like you said, the real-world sensors measurements, that's often analog, right? Continuous signals.
Precisely. Temperature, pressure, flat position. These are usually analog signals, varying smoothly. To get them into the digital world for the computers to process, you need an analog-to-digital converter, an ADC.
Okay. And how does that work, basically?
Well, the ADC essentially takes snapshots or samples of the analog signal at very regular fast intervals. Then for each sample, it assigns a digital number. It quantizes it based on the signal's amplitude at that instant.
So it turns that smooth wave into a series of discrete steps, digital values.
You got it. A stream of digital data points that the computer can understand and manipulate.
Right. And then going the other way, when the computer needs to, say, move a control surface or drive a gauge.
That's the job of the digital to analog converter, the DAC. It does the reverse. It takes that sequence of digital numbers from the computer and reconstructs an analog signal from them. It often works by generating tiny impulses based on the digital values, and then those impulses are smoothed out by a filter to create a continuous-looking analog output.
Like connecting the dots, but smoothly.
Sort of, yeah. The module mentions the MC1408. That's an 8-bit DAC. That 8-bit tells you the resolution, how many distinct voltage levels it can create. 2 to the power of 8, which is 256 steps. That analog output can then drive an actuator or maybe an older analog-style cockpit instrument.
Okay, clear. And just quickly, the module mentions DC and AC analog signals. The difference.
For our purposes, think DC direct current as unipolar. It varies, but always stays either positive or negative relative to a zero reference, like a slightly fluctuating battery voltage.
Okay.
AC alternating current is usually bipolar. It swings both positive and negative around that reference point, like a sine wave. Different sensors, different systems use one or the other.
Got it. Okay, that lays the groundwork.
Yeah.
Now, how does all this digital information actually get from one system to another around the aircraft? Data buses, right? This seems huge.
Oh, absolutely critical. Think about older aircraft, miles and miles of individual wires connecting everything point to point. Hugely heavy, complex, so many potential failure points.
Nightmare to troubleshoot, I bet.
You bet. Digital data buses changed all that. They're basically shared communication highways. Multiple systems can connect to the same bus to send and receive data, drastically cutting down on wiring, weight, and complexity, and improving reliability. Data travels serially, bit by bit, along the common path.
Okay, so let's break down the types mentioned. First up, MLSTD153B. What are the key takeaways for that one?
Right, 1553B. Key things. It's asynchronous, meaning no single clock timing everything. And it's half duplex data goes both ways, but only one way at a time. Think walkie-talkie.
Okay, push to talk.
Exactly. There's always a bus controller, the BC, which is the boss. It initiates all communication. Then you have up to 31 remote terminals, or RTs, which are the interfaces to the actual subsystem, like a sensor or an actuator controller.
Right.
And often there's a bus monitor, the BM, just listening in, recording traffic for diagnostics or analysis. The crucial thing is the command response protocol. BC sends a command, only the addressed RT responds. It's very structured.
And connections, direct or transformer.
Both are used. Direct coupling for short runs, but transformer coupling is very common. It gives you electrical isolation, which is great for preventing noise and ground loop issues. So if a 1553 system isn't talking, checking that command response sequence is step one. Is the BC even sending commands? Is the RT responding?
Got it. Controlled, one boss. Now, AirNC 429. How's that different?
Simpler. AirNC 429 is simplex. Data only flows one way.
Like a hose pipe.
Good analogy, yeah. One transmitter talking, potentially multiple receivers listening on that same wire pair. It's very common for, let's say, sending data like altitude from one source to several different displays or computers that need it. Generally lower side than 1553.
Okay, one-way street. And then the module mentions the AirNC 629, specifically on the Boeing 7777. Sounds like a bigger deal.
It is, yeah. A significant step up. Much faster data rate, 2 megabits per second, and it can handle way more terminals, up to 131. The big difference from 1553 is there's no central bus controller.
Ah, okay. How does that work then? Chaos.
Huh? No, it's clever. It's a multiple source, multiple sync setup everyone can potentially transmit. But it avoids collisions using a strict time-based protocol. Each terminal gets specific, pre-assigned time slots when it's allowed to transmit.
Time division multiplexing, sort of.
Exactly, but built into the bus protocol itself for collision avoidance. Each terminal connects via a serial interface module, or SIM, which handles the electrical interface and manages that timing. So troubleshooting on a 777 might involve checking if a terminal is transmitting in its correct slot.
Right, like a very organized, high-speed highway with designated on-ramps. What about the newer stuff? Aircraft networks, Ethernet, ARNC 664.
Yeah, that's the evolution. Moving towards full duplex, sending and receiving at the same time, like a phone call, and leveraging standard networking tech like Ethernet, but with critical enhancements for aviation.
Enhancements like?
Determinism, guaranteed delivery times, guaranteed bandwidth. That's what ARNC 664 AFDX Avionics full duplex switched Ethernet provides. It uses virtual links to reserve resources and ensure that critical data gets through reliably and on time, even on a busy network. You see these used for really high bandwidth needs video, massive data transfers between integrated modular avionics systems, much more flexible and powerful.
Amazing how that data flies around. Okay, let's shift focus a bit. Back to the processing the tiny building blocks, logic gates, and basic computer structure.
Right down to the fundamentals. Logic gates are the absolute base level. Tiny electronic circuits, usually built with transistors, that perform a basic logical operation, A and D, or not T, etc. They take binary inputs, zeros or ones, and produce a single binary output based on that logic rule.
The decision makers.
Exactly, the tiny switches controlling the digital flow.
And these individual bits, they get grouped together, right? Bytes and words.
Correct. A single bit isn't much use on its own, so we group them. A byte is typically 8 bits. And bytes are often grouped into words. That's the standard chunk of data that a specific computer's processor, the CPU, is designed to handle at once. Could be 16 bits, 32 bits, 64 bits. Depends on the architecture.
Okay. And these words can be instructions or data.
Yep. Instruction words tell the CPU what to do, add, subtract, move data. Data words are the actual numbers or values being worked on.
So what are the main parts of a computer using these gates and words?
You boil it down, there are 3 core parts. The CPU central processing unit, the brain, executes the instructions. Main memory stores the instructions and data the CPU needs quick access to. And the input-output system, the I/O, that's how the computer talks to everything else. Sensors, actuators, other computers, displays.
And in main memory, we hear about RAM and ROM. What's the key difference for someone doing maintenance?
The big one is volatility and what they're used for. Random access memory is volatile. Power off, data gone. It's the computer's workspace. It's short-term memory. Super fast for reading and writing, which is why the CPU uses it for active calculations. ROM read-only memory is non-volatile. It keeps its data even with no power.
Okay, permanent storage.
Right. Used for stuff that shouldn't change often, like the initial boot-up program or basic system firmware. Now, there are variations you'll see mentioned: PROM, EEPROM, flash memory. These offer different ways to program or reprogram that permanent storage.
Like for software updates?
Exactly. Flash memory is very common now for storing things like operational flight programs, OFPs, in avionics boxes. These need to be persistent, but also updatable in the field. So if a system forgets its settings after you cycle power, you might suspect an issue with its non-volatile memory.
Good tip. Okay, ROM for prominence, RAM for work, and all this stuff is built on integrated circuits ICs. What are they, practically speaking?
An IC, or chip, is basically a whole electronic circuit: transistors, resistors, capacitors, all interconnected, shrunk down, and manufactured on a tiny piece of semiconductor material, usually silicon.
Tiny is right.
Oh, yeah. We're talking millions, even billions of components on something smaller than your fingernail. That's what makes modern electronics possible, powerful, and compact. You might hear terms like TTL or CMOS. Those just refer to different families of transistor technology used to build the ICs. They have different power and speed characteristics.
And this density just keeps increasing.
Exponentially, historically. That's Moore's law, basically. But it also means these components are incredibly delicate, especially regarding static electricity, which we'll get to.
Right. And a microcomputer that's essentially taking all this and putting it on one board.
That's the idea. A microcomputer system fits on a single board, often called a motherboard. It's got the microprocessor, the CPU chip, memory, RAM, and ROM, and the I/O interfaces all together. Its performance depends on things like clock speed, how fast it runs instructions, and word size, how much data it chews on at once.
Okay. Can you give an example of a microcomputer system in an aircraft context?
Sure. A classic example is the flight management computer, the FMC. That's a dedicated computer managing the flight plan, performance calculations, fuel predictions, all that. Its peripherals would be things like the cockpit displays, where you see the route, the CDU control and display unit, the keyboard and screen the pilots use to interact with it, and maybe a data transfer system for loading navigation databases or software updates.
And there are usually two FMCs, right, for redundancy?
Absolutely. Often dual FMCs, dual CDUs. Redundancy is critical for flight safety. So if a pilot reports they can't enter data, the problem could be the CDU, the FMC itself, or the connection between them.
Makes sense.
Oh, right.
Okay, let's dig into that microprocessor heart a bit more. How does it actually work, cycle-wise?
The basic operation is a constant loop called the machine cycle. It fetches an instruction from memory, decodes that instruction to figure out what operation is needed, executes the operation using its internal units, and then stores the result, maybe back in memory or in an internal register. Fetch, decode, execute, store, over and over, incredibly fast.
Synced by a clock.
Exactly. A very precise clock signal orchestrates every step.
And inside, what are the key parts doing the work?
You've got the control unit, which is like the traffic cop, managing the fetching and decoding and telling everyone else what to do. Then the ALU arithmetic logic unit, that's the number cruncher, does all the math and logical comparisons. You've got the clock, providing the heartbeat, and registers small, super fast, temporary storage spots right inside the CPU for holding data that's being actively worked on.
Okay. The module also mentions encoders and decoders. What do they do in practice?
They're like translators between different digital formats. An encoder takes multiple input lines and converts them into a coded output, usually with fewer lines. Like an 8-line to 3-line encoder might output a 3-bit binary code telling you which of the 8 inputs is active, useful for things like keyboard scanning or priority signals.
Condensing the information.
Right? And a decoder does the opposite. It takes a coded input, maybe a binary address, and activates one specific output line out of several. Like a 2-line to 4-line decoder uses a 2-bit input to select one of 4 outputs. The text mentions the 74138 chip. That's a common 3-line to 8-line decoder. You'd use a decoder to select a specific memory chip or maybe route data to a particular device. And that 74138 also has enable lines, which let it act as a demultiplexer too.
Okay, encoders code, decoders select. What about multiplexing and demultiplexing then? Sounds related.
Very related. Multiplexing or muxing is about sharing. It takes multiple input signals and selects one of them to send down a single output line. Think of it like a rotary switch connecting one of several inputs to the output, controlled by select lines.
Okay, funneling multiple streams into one.
Exactly. Saves wiring. You might send data from several sensors over one data bus using a multiplexer. The module mentions the 74153 MUX chip. Then at the other end, you need a demultiplexer demuxing. It takes that single input line and distributes it to one of several possible output lines, again based on select lines.
Sending the shared signal to the right place.
Precisely. And as we mentioned, a decoder like the 74138 can often be used to control the select lines of a demultiplexer. Time division multiplexing, TDM, is a common technique where different signals get assigned different time slots on the shared line.
Everyone gets their turn on the channel.
Right.
Got it. And the scale of integration you mentioned earlier, SSI, MSI, LSI, leading to billions of transistors now. What does that really mean for us?
It means incredible capability packed into tiny spaces. We went from small-scale integration, SSI, with just a few gates, to medium-scale MSI with basic functions like counters, to large-scale LSI giving us early microprocessors and memory. Now we're at VLSI, very large scale, and beyond, system on chip, so where practically an entire computer system is on one piece of silicon.
Moore's law in action.
Absolutely. The upside is amazing power and miniaturization. The downside, well, troubleshooting individual transistors is impossible. You replace the whole chip or module. And all that density generates heat, so cooling, heat sinks, airflow become really critical maintenance considerations. Plus, these tiny structures are super sensitive to ESD.
Which is a perfect segue. Let's talk about transmitting data another way. Fiber optics. How does that compare to good old copper wire?
Big advantages for fiber in many aircraft applications. Instead of electrical signals down copper, it sends pulses of light down thin strands of glass or plastic. Benefits? Huge data rates, massive bandwidth carries way more info, very low signal loss over distance, totally immune to electromagnetic interference, EMI, which is a huge plus in the noisy electrical environment of an aircraft, and significantly lighter than copper cables for the same capacity. Weight saving is always good in aerospace.
Sounds almost too good to be true. Downsides.
Well, cost can be higher for the cables, connectors, the light sources, and detectors. And working with its splicing, terminating fibers, it's more delicate, needs specialized tools and training compared to stripping and crimping copper wire.
Makes sense. How is the cable actually built to guide light like that?
It's layered. In the middle is the super thin glass or plastic the light travels down. Around that is the cladding, another optical material, but with a slightly different refractive index. Okay, that difference causes light hitting the boundary at shallow angles to reflect back into the core total internal reflection. It keeps the light trapped inside. Then you've got buffer coatings for protection, strength members may be made of Kevlar, and an outer jacket for overall toughness.
So there. And the light source and detector.
On the transmitting end, usually an LED, light-emitting diode, or a laser diode. Lasers give you higher speed and power, better for long distances or really high data rates. On the receiving end, a photodiode converts the light pulses back into electrical signals for the electronics.
Okay. The module differentiates single mode and multi-mode fiber. What's the key there?
It's about the core size and how the light travels. Multi-mode has a larger core. Light can bounce around taking multiple paths or modes down the fiber. It's simpler, cheaper, good for shorter distances, but the different path lengths can cause the light pulses to spread out, limiting speed. Single mode has a tiny core, like incredibly thin. It forces the light to travel pretty much straight down the middle in a single path. This minimizes that pulse spreading, so you can go much further and at much higher data rates. Think long-haul communications, high bandwidth backbones.
Got it. And connecting these fibers in a network. Couplers.
Yep. Couplers split or combine light signals. You have simple T-couplers, directional couplers, and star couplers. A star coupler has multiple inputs and outputs, good for distributing a signal to many points. The nice thing about star couplers is the loss usually doesn't stack up as badly as with T-couplers when you add more terminals.
Okay.
You also have optical switches in some advanced networks, like AFDX, that can actively route light between different fibers. And key terms to know are attenuation, the signal loss as light travels down the fiber, and termination, making sure the fiber ends are perfectly prepared and connected to minimize reflections and loss. Bad terminations are a common source of problem.
Right. Critical details. Okay, moving from data travel to data presentation, electronic displays. Big change from the old steam gauges.
Huge change. Those old, bulky, power-hungry CRTs, cathode ray tubes, are pretty much gone from new designs, replaced by flat-panel, solid-state displays, primarily LEDs and LCDs.
We mentioned LEDs for fiber optics. How do they work in displays?
Same basic principle, electroluminescence. Pass current through the right semiconductor, light comes out. Different materials give different colors. They're great for simple indicator lights, numeric readouts, and crucially, as the backlight for LCDs. They're bright, efficient, long-lasting. Making a full high-res display purely from tiny individual LEDs has been trickier, though getting better.
So LCDs are the main tech for the big cockpit screens.
Generally, yes. Liquid crystal displays. Key thing. They don't emit their own light. They control the passage of light from a backlight, often LEDs, like we said.
How do they control light?
They use liquid crystal molecules, which have the neat property of aligning themselves to an electric field. These crystals are sandwiched between glass plates with microscopic grooves and polarizing filters. Without a voltage, the crystals twist the light's polarization so it can pass through the second filter. Apply a voltage, the crystals untwist, blocking the light.
Wow. So you control the voltage pixel by pixel.
Exactly. By controlling the voltage across tiny segments or pixels, you create light and dark spots forming the image.
And the module mentions passive matrix versus active matrix LCDs. What's the important difference for flight decks?
Performance, mainly. Passive matrix uses a simpler grid to address pixels. It's cheaper, but can be slow to respond, have lower contrast, maybe some ghosting. Active matrix LCDs or AMLCDs, especially those using thin film transistors, TFTs, are much better. Each pixel gets its own little transistor switch right there on the glass. This allows much faster, more precise control of each pixel individually. Result: faster refresh rates, much better response time, critical for showing rapidly changing flight data, sharper contrast, wider viewing angles. AMLCD with TFT is the standard for modern electronic flight instrument systems.
Right, that clarity and speed is essential.
Huh.
Okay, we've got data represented, moved, processed, displayed. Now protecting it all. Electrostatic discharge ESD. Sounds staticky.
It is, and it's a huge deal in electronics maintenance. ESD, electrostatic sensitive devices. Modern chips, with their incredibly tiny internal structures, are really vulnerable to damage from static electricity.
How does it build up, just walking around?
Yep. Friction is the main culprit, especially in dry air. Walking across a carpet, sliding a plastic box, even just moving around in synthetic clothing can build up thousands of volts on your body without you even feeling it.
Thousands, really?
Oh yeah, easily. Then, if you took a sensitive electronic component, zap.
And that zap is the discharge. How does it damage the part?
That sudden transfer of charge, the ESD event, creates a very brief but intense pulse of current and heat right inside the microscopic circuitry. It can literally melt or vaporize tiny connections or puncture insulating layers. It might cause immediate total failure or worse, latent damage, a hidden weakness that causes the part to fail later, maybe in flight.
Scary. And electrostatic induction.
That's where a charged object nearby can cause charges to redistribute within an uncharged component, potentially creating damaging voltages even without direct contact.
Yeah, so how sensitive are these parts? The module mentions classes.
Right. Standards classify devices by the ESD voltage level they can withstand. Class 0 is the most sensitive, damaged by less than 250 volts. Class 3 might handle up to 8,000 volts. A lot of modern avionics components are down in those more sensitive classes, and they're getting more sensitive as things get smaller. That's why the precautions are so strict.
So what are the absolute must-do precautions when handling these things?
It's a whole system approach. First, designated static safe workstations, conductive floor mats, conductive table mats, all connected to a common ground point, usually through a 1 megaohm resistor, just for safety, to limit current if something goes wrong.
Okay. Grounded surfaces.
Then the technician must be grounded too. That's the wrist strap. It connects you to that same ground point, again through a safety resistor, constantly draining any charge off your body.
Nowhere the strap.
Every time. And you should test the strap and the workstation grounds regularly with a dedicated tester to make sure they're working. Ionizers can also help. They blow ionized air to neutralize static charges on insulating materials that you can't ground, like plastic casings or paperwork.
What about moving parts around?
Always transport ESD-sensitive items in proper shielding bags or containers. These bags have a conductive layer that forms a Faraday cage, protecting what's inside. Keep them in the bag until you're at the grounded workstation and you are grounded yourself. Before you touch the component itself, touch the grounded mat first to ensure you're at the same potential. Use grounded tools like soldering irons, and store components properly in those shielded bags on grounded racks or shelves. It's all about preventing that charge difference and sudden discharge.
Seems thorough, but absolutely necessary. Okay, switching gears again, software. Millions of lines of code in these planes now. Software management control must be critical.
Beyond critical. It's absolutely paramount. Think about it. Software controls flight surfaces, navigation, engine parameters. An unapproved change, a bug introduced during an update, could be catastrophic. Imagine a failure during a low visibility approach.
Yeah, nightmare scenario. So how is it controlled?
Through extremely rigorous processes covering the entire software lifecycle planning, development, verification, validation, configuration management, modification. Everything has to be meticulously defined, documented, and followed.
Lots of paperwork, I assume.
Tons. Airworthiness plans, quality assurance plans, configuration management plans, verification plans. It's all about ensuring traceability, proving the software does exactly what it's supposed to do and only what it's supposed to do under all conditions.
The module brings up DO-178. What is that exactly?
DO-178 is the standard for software safety in aviation, recognized globally by FAA, EASA, everyone. It establishes different design assurance levels, DALs, from A down to E. Based on how bad the consequences would be if the software failed. Level A is for software where failure could be catastrophic, think primary flight controls, core navigation. Level E is for software where failure has no safety impact, maybe like some cabin entertainment functions.
And the higher the level, the stricter the process.
Massively stricter. Level A requires the absolute highest degree of rigor in development, testing, verification, documentation, proving its safety integrity.
Okay, and AirINC 653, how does that fit in?
AirINC 653 is about the operating system environment, particularly for integrated modular avionics, IMA. That's where you have multiple software applications, potentially with different criticality levels, different DALs, running on the same processor hardware.
Sharing resources.
Right. ARNC 653 provides strict partitioning rules that guarantee memory space and processing time for each application, completely isolating them. So a glitch in a low criticality application, say level D, absolutely cannot interfere with a critical level A flight control function running on the same chip. It ensures freedom from interference.
Vital for IMA. The module also mentioned the DO-178 evolving from B to C with supplements. Why the updates?
Technology marches on. DO-178C from 2011, and its supplements were needed to address newer software development techniques that weren't common when DO-178B was written. Things like model-based development and verification, that's DO-331, using object-oriented programming languages, DO-332, formal methods which use mathematical proofs, DO-333, and also qualifying the software tools used in development, DO-330. If you're relying on a tool to automatically generate code or run tests, you need to prove the tool itself is reliable.
Makes sense. Tools can have bugs, too.
Exactly. DO-178C also really strengthened the requirements for traceability, being able to link every requirement down through the design, the code, the tests, and back again. The level of detail required for this tracing gets much higher for the critical DALs. You hear terms like red trace, purple trace, denoting very specific, complete coverage analysis needed for level A.
Incredibly rigorous, as it should be. Okay, let's consider the environment these systems live in, the electromagnetic environment.
Right. Aircraft are complex electrical environments, lots of signals flying around, both intentional and unintentional, and external sources, too. Any electromagnetic energy can potentially interfere with sensitive electronics if it's not managed.
Starts with basic physics, right? Current and magnetism.
Yep.
Any electric current creates a magnetic field. The right-hand grip rule helps visualize it. Point your thumb along the wire in the direction of current, and your fingers curl in the direction of the magnetic field lines around the wire.
Okay. And how does this energy cause interference? Coupling mechanisms.
4 main ways energy gets from a source to a victim circuit. Conductive coupling interference travels along shared wires like power or ground lines. Inductive coupling, a changing magnetic field from one wire, induces a voltage in a nearby wire, like a transformer. Capacitive coupling, changing electric fields, transfer energy between nearby conductors separated by an insulator, like a capacitor. And radiative coupling energy travels through the air as electromagnetic waves, like radio waves.
Got it. And EMC versus EMI. EMC, electromagnetic compatibility, is the goal. It means a piece of equipment works properly in its environment without causing interference to other things, controlling its emissions, and without being disrupted by interference from other things, having sufficient susceptibility or immunity. EMI, electromagnetic interference, is the problem, the unwanted energy causing the disruption.
What about HIRF, high-intensity radiated fields? Sounds serious.
It is. These are very strong external electromagnetic fields, maybe from powerful radar sites or broadcast towers. There's concern they could potentially overwhelm aircraft shielding and interfere with critical systems, especially flight controls. Regulations require aircraft to be protected against HIRF.
And lightning, obviously a major hazard.
Huge potential energy. The aircraft are designed with lightning protection. The connective airframe acts like a Faraday cage. Bonding straps ensure paths for current to flow safely. Static wicks help dissipate charge buildup to make a direct strike less likely. But it's still a major consideration, especially with more composite structures, which are less conductive than metal.
Right. Composites change the game a bit.
They do. And modern digital electronics, with their low voltage levels and fast signals, can be more susceptible to EMI in general. That's why the technician's role is vital. Proper installation, ensuring shielding is intact, like LRU cases being properly closed and grounded, using correct bonding and grounding techniques, it's all part of maintaining the aircraft's overall EMC. Reassembling an LRU incorrectly might compromise its shielding.
Attention to detail is key. Okay, finally, let's pull it all together. What are some typical electronic digital systems where we see all this technology at work?
Modern aircraft are packed. You look in the avionics bay of something like a 777, it's just racks of equipment. Flight controls, inertial systems might be down low, cabin systems in the middle, comms, nav, surveillance up top.
So specific examples, EFIS.
EFIS, Electronic Flight Instrument System, that's your main PFD, primary flight display, and ND, navigation display. Big glass screens replacing dozens of old instruments, driven by symbol generators that process sensor data and draw the displays.
EASA or ECAM.
Engine Indication and Crew Alerting System, Boeing's IACs, or Electronic Centralized Aircraft Monitor, Airbus's ECAM. These monitor engines and aircraft systems, show parameters, and provide warnings or alerts on dedicated displays or MFDs, multifunction displays. Huge safety enhancers. And highly redundant, often triple redundant displays and processors. Integrated modular avionics, we mentioned it with Aaron's C653. It's an architecture where common computer modules run multiple different applications, sharing resources to save weight and power and improve flexibility.
ECARS.
Aircraft Communication Addressing and Reporting System. It's a digital day-link system for sending short messages between the aircraft and ground airline operations, maintenance data, automatic reporting of flight phases like out, off, on, in times, OOO.
ORS.
Inertial Reference System. Uses gyros and accelerometers to sense motion, rotation, and acceleration. From that, it calculates the aircraft's attitude, heading, velocity, and position. Modern ones are strap-down systems using laser gyros or other solid-state sensors feeding data to computers rather than complex mechanical gimbaled platforms.
But they drift, right?
They do. Integration errors build up over time. That's where GPS comes in.
Global positioning system.
Exactly. Gets positioned from satellites. Much more accurate long-term, but the signal can be blocked or interfered with. So, modern systems blend IRS and GPS data, often using Kalman filters, to get the best of both the smooth, high-rate output of the IRS, corrected by the long-term accuracy of GPS. Augmentation systems like WESA-S improve GPS integrity and accuracy too.
FMS.
Flight management system. The brain of the operation, often dual FMCs and CDUs, integrates navigation data, performance data, flight plan, helps pilots fly optimized routes, manage fuel, automate tasks.
CCAs.
Traffic alert and collision avoidance system. Actively interrogates transponders on other nearby aircraft. If it detects a potential collision threat, it issues a traffic advisory, TA, traffic, or, if it's urgent, a resolution advisory, climb, or descend, telling the pilot how to maneuver vertically to avoid the other aircraft. Crucial safety system. Automatic dependent surveillance broadcast. This is a big part of next-gen air traffic control. Aircraft automatically broadcast their precise GPS-derived position, altitude, velocity, etc. to other aircraft, ADS-B and equipped, and ground stations. Improves situational awareness for everyone, allows for more efficient routing, uses 1090 MHz extended squitter or UAT frequencies, emergency locator transmitter, battery-powered beacon activated automatically by crash forces, G-switch, or manually, transmits a distress signal on 406 MHz picked up by the COSPAS SARSAT satellite system. Modern 406 ELTs include GPS position data and aircraft registration info in the signal, drastically speeding up search and rescue. Some are portable, too.
Wow. And fly-by-wire? cabin systems.
Yep. Fly-by-wire replaces heavy mechanical cables and pulleys with electrical signals to control flight surfaces. And cabin systems, in-flight entertainment, Wi-Fi, even onboard cell phone capability via satellite links, SATCOM. These use sophisticated servers, communication managers, and often high-speed data buses like FireWire or Ethernet running through the cabin. It's all interconnected.
That's an incredible range of systems, all relying on the digital and electronic principles we've discussed.
It really is. We've gone from the basics of binary and logic gates through data buses, computer guts, fiber optics, displays, handling precautions like ESD, the vital software controls, the electromagnetic environment, and finally seen how it all comes together in these complex systems you work with.
Yeah, hopefully this deep dive, drawing on that EASA material you sent, has given you, our listener, a clearer, more practical handle on this electronic landscape in aircraft maintenance.
We hope so. It's fundamental knowledge for anyone working on modern aircraft.
Absolutely. And maybe a final thought to leave you with.
Hmm.
Well, just consider how this constant increase in integration and complexity impacts what you do. How does it change troubleshooting? What does it mean for the future? Maybe things like predictive maintenance using all this data or new diagnostic tools. Something to chew on.